Hello and welcome to the presentation of our transaction paper, Signal Selection for Oscillation Monitoring with Guarantees on Data Recovery Under Corruption. I'm Kaustav Chatterjee, and this paper has been co-authored with my advisor, Dr. Nilanjan Rajouri from Penn State, and Dr. George Stefopoulos from the New York Power Authority.
Often in PMU signals, we encounter sustained missing data, spurious outliers, and other forms of data anomalies. This may adversely affect the performance of estimation, monitoring, and control algorithms. In our previous work, we have proposed a robust PCA-based anomaly detection and data recovery approach as shown in the figure. This pools measurement data from multiple PMUs and solves a lasso-type convex optimization to recover clean data from corrupted samples. Going ahead, in this work, we explore under what conditions is this recovery exact and always guaranteed. Looking back into the literature of compressive sensing, it is well established that if the restricted isometric constant of the complementary projection matrix is below a particular threshold, then exact recovery is guaranteed. In this work, we try to understand the physical interpretation of this restricted isometric constant in the context of power systems. We derive an analytical relationship between the RIC and the relative modal observability of the PMU signals and use the latter for calculating the first. Our primary proposition is that if we can group the PMU signals by minimizing the variance in the modal observabilities for each poorly damped mode, then we can arrive at a lower RIC and therefore attain the threshold desired for guaranteeing exact recovery. In other words, a dense signal set implies lower RIC of the complementary projection matrix. Next, we lay out a methodology for doing the same. Starting with a block of previously recovered samples, we perform modal estimation to obtain the mode shapes of the signals for all poorly damped modes in the system. Next, using mode shapes as features, we use clustering algorithms for grouping the PMU signals. At this point, it is worth noting that recovery in each group is separate from another, and grouping or clustering happens only at infrequent intervals. In other findings, we mathematically deduce that for a sufficiently dense group, modal observabilities are in phase, and denseness decreases linearly both with increase in the variance of the observability magnitudes and increase in the magnitude of the largest observability. This can have profound implication in signal selection for oscillation monitoring. Finally, we present some case studies on real PMU data. We use 40 PMU signals from New York Power Authority. 2 of the groups formed out of these 40 signals are shown in the figure. Notice each group has a distinct frequency content and as seen in their respective PSDs. In the figure, we show a group of 8 signals for each group. We show the corrected signal, the actual signal, and the corrupted signal. In each group, we corrupt 2 signals with missing data and chattering noise. It can be seen that the recovery is good in the respective cases. In summary, we can conclude that any arbitrary grouping may not ensure good recovery. As seen in the example, it leads to poor quality estimation and might result in incorrect decision making. Finally, increasing the number of signals is not enough for guaranteeing anomaly resilience. This brings us to our proposition on signal selection, and that grouping by minimizing variance in the observabilities can guarantee exact recovery. Finally, since recovery in each group is independent, this has merit to be implemented in a decentralized fashion for distributed anomaly detection and correction. Thank you. For further details, you may look into the paper listed here. Thank you.